Sorry, say that again.
You may be talking to the wrong meeting.
Yes. Yeah. When you said you're not sure.
No, this is the connectivity meeting here, AWHI. So if you're not speaking, I might encourage everybody to put yourself on mute. And Noah, do you want to go ahead and kick us off and we'll get rolling?
Yeah, absolutely. Can you see my screen okay, Jeff?
Yep. You're
Perfect. All righty. Well, it looks like we have some great attendance today. Thanks everybody for showing up. So with that said, our agenda is fairly short today. I wrote an email to you all out yesterday that we had another presenter.
I mean, we'll see what kind of changes they're asking for them, whether or not they affect the pricing.
Gabriel, can you mute yourself?
We'll figure.
I just did.
Yeah, so we had another presenter today as well, Karen Finale from the FSEC, but unfortunately with Hurricane Milton hitting Florida right now, she's unable to attend, but we're stoked to have Pierre here still, so that's excellent. So just going to go through a quick couple AWHI updates, and then we will get into Pierre's presentation and leave some time for Q&A at the end. So big thing here is Heat and Water Heater Day. We have a lot of folks who regularly attend this call presenting, including Jeff, Peter Grant's also presenting. Amelie is presenting as well. So definitely look forward to having you all there for connectivity things, as well as other residential and central heat and water heater topics. And we'll probably have some fun times for my colleague Joe Wachunas in a brand new heat and water heater costume. So definitely looking forward to that. And along those lines, if you haven't caught Joe's article about his tour across America yet, so Joe runs a bunch of the other AWHI working groups, and he took an awesome trip all the way from the Midwest back to where he lives in Portland, and made a bunch of cool stops along the way at various heat pump water heater factories and meeting with manufacturers. So definitely check that out. And he convinced the manufacturers to do some heat pump water heater dance-offs with him while he was in his costume. So definitely don't want to miss that. I think it's just a really great example of bringing heat pump water heaters into the main kind of limelight. Whereas, besides us, a lot of folks aren't thinking about their water heaters on a regular basis. So just making it fun, raising awareness, all really good stuff. Sorry about that. So, sorry. With that, I'm actually going to turn it over to Pierre, unless Jeff or Tristan has any AWHI related updates they want to share.
Do you have the antitrust slide handy?
Oh, yes, the antitrust slide somehow got disappeared from this one. So that is a great point. I do have it on another meeting. So let me pull that up really quick.
Okay, and while you're doing that, perfect. Can everybody remember to put their name, their title, and their organization in the chat while we're going through there? And I'm going to call on Dana Bradshaw, colleague of mine at NIA, to read the antitrust statement, please.
I would love to, as long as everyone can hear me.
We can.
Indeed.
Good.
All righty there, here we go. The Advanced Water Heating Initiative is a member-supported collaborative of professionals from across the U.S. This diverse membership includes numerous competitors, and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times, and this and other AWHI meetings, participants should not discuss competitive pricing, profitability, allocating markets or customers, or promotion of a particular product or accessory.
Great.
Thank you so much.
Mm-hmm.
All right, I'm going to stop sharing here, and I'll allow Pierre to share his screen and dive into the presentation.
Well, let me do a brief introduction of Pierre. If you don't know Pierre, Pierre has been in this space for more than 20 years, probably close to 30 in the energy efficiency world. I've had a great pleasure to work with him long ago on several initiatives regarding the efficiency of power supplies and desktop computers. He was formerly with NRDC, and now he is working on a new project mostly focused on the California market at this point, but he's got some great innovation that integrates not only heat pumps, but also controllability. So I I've had a really great chance to work with Pierre over the years. He's a runner, a competitive runner. So if he says, "Hey, let's go for a jog," you might want to make sure you're prepared. In any case, Pierre, take it away. We're looking forward to your presentation.
Thank you, Jeff, and thank you everyone for the opportunity to present here. I think I was on this committee maybe about a couple of years ago before wearing my NRDC hat, and I'm glad to see the committee is still doing well and moving the connectivity mountain. Hopefully it's no small hill now, and so we're getting over that hill and getting to deployment now. So I want to give you a little bit of background on the technology before we talk about connectivity itself. I know this is the main topic today, but I think to put in context of what is the application that is connectivity enabled and how are we able to get this amount of load shifting and grid value and customer value from it. So Harvest Thermal, in a nutshell, we integrate thermal energy storage with an air-to-water heat pump to provide both heating and hot water in a demand-flexible manner. And our goal is really to use thermal energy storage to make heat pump operating costs more affordable and to help scale heat pump adoption. So let's start with a quick reminder that heating and hot water together, on average in the US, is about 62% of residential energy use. Across both fossil fuels and electricity, it's nearly 2/3 of home energy use. And if we can, with one system and one thermal battery, make these two end users flexible, we basically made nearly 2/3 of the home energy use flexible. So that's the realization that led to the founding of Harvest Thermal, is how to deploy a solution that will enable this amount of load flexibility in residential homes. And by doing it with a combination system, integrated system, whatever the terminology, we are able to reduce costs by giving access to customers with one device to both end users and make those both end users flexible. So how do we do this? The system architecture is basically a split heat pump water heater, but it could be an air-to-water heat pump. It doesn't have to be specifically a heat pump water heater. A humble hot water tank that is managed as a thermal battery with a controller. So the Harvest Thermal device is really that controller, that magic box next to the tank, which is both a hydronic controller. So imagine a hydronic system in a box, assembled and tested at the factory, so it's just easy to install on site. It's basically plug and play, and it makes hydronic systems cost effective to install. It's also an electronic controller, more the brains of the system, in that it has all the functions needed to manage the heat pump water heater as a thermal battery. It monitors its state of charge. It's the kind of thermodynamic model of the stratification in the tanks. We know the state of charge in the tank at any point in time, just like you know the state of charge of your laptop or your phone. And knowing that state of charge allows us to manage the charging and discharging of that thermal battery, just like any battery device. The Harvest Pod also monitors and predicts demand, both heating and hot water demand, by monitoring when people use heating and hot water, correlating that with the weather, and then using the weather forecast, estimating or predicting the thermal demand for the next 24 hours. So now you have a 24-hour demand forecast, you have a day-ahead price forecast, you may have a day-ahead greenhouse gas forecast, and you have an optimization algorithm that says, okay, I'm going to need that much heat and hot water at this time in the next 24 hours, at those times in the next 24 hours. What is the optimal time to charge the thermal energy storage? By how much? We don't fully charge it all the time. In summer, we're going to charge maybe 30% of it. In winter, we're going to charge it twice over, morning and evening. So we minimize thermal energy, thermal losses. We minimize how long the hot water remains in the tank, because thermal losses are proportional to time, storage time. So it's basically an optimization algorithm that is based on forecasting demand, price forecast, or day ahead price signals, And that allows us to optimize for efficiency and to optimize for cost whenever you have time of use rates or time differentiated pricing, which I know is not everywhere yet, but it's getting more common as we are moving towards a more decarbonized grid. Actually, most utilities have, at least the top utilities, all have time of use rates as opt-in, even if it's not always default. California now they're by default, and you can opt out. So we are slowly moving to getting more and more utilities having time of use rates. And now the next frontier is actually hourly dynamic rates. And we're starting to see this in California and in other places as well. So it's really about how do we maximize that opportunity to be able to heat and provide hot water at a much lower cost when you have time differentiated pricing. And we know that this is a heat battery in the sense this is a water heater and the tank is used as a heat battery. It doesn't do chilled water storage, but we know that people do need cooling. The majority of customers will need cooling, and we want to make sure that we can fulfill that need. So what we do is we integrate with either an existing air conditioner or heat pump or a new air conditioner or heat pump, and we integrate in the same air handler with a separate coil, a DX coil. So the air handler has both a hydraulic and a DX coil. And we control that second heat pump so that we can shift its load off peak by using thermal energy storage. So that second or auxiliary heat pump or AC heat pump is both a source of cooling and supplemental heat to back up or to supplement the hydraulic system where extra capacity is needed. So that's the architecture of the system, the principle of the system. What this is doing is really shifting load away from peak times on the grid, so peak cost and emissions times. Here you have the shape, it happens to be the California duck curve that everybody's familiar with, but this is really the shape of any grid that has significant solar, and this is where the whole, most regions are moving to as we are expanding solar on the grid, and wind to some extent. But wind is more variable in time, whereas solar, the sun always shines at the same time in the day. And we know that heat pumps, while they're wonderful machines from an efficiency perspective, they also tend to operate when it's coldest, which is winter mornings before sunrise, and winter evenings after sunset when there is no solar energy available on the grid. And this reduces both their, GHG reductions, their efficiency, because these times tend to be colder, so lower COPs. So what we do with the thermal energy storage on Harvest is we are able to reshape that load, run the heat pump when energy is cleanest and cheapest in the middle of the day and when it's most efficient, and store that energy, that clean and cheap energy in a thermal battery, and use that thermal battery to offset and the peak time energy use from the grid and from energy bills. So that has grid benefits, especially in regions that are winter peaking or are going to be winter peaking. That's nearly half of the states and utilities in the country are already or moving towards being winter peaking as we electrify more homes and vehicles. And and I think the Pacific Northwest in particular, I know we have a lot of, NIA is hosting this, and in the winters, before the snow melt season, I know that the hydro system is low, and you tend to have, the grid tends to be more constrained, and energy prices tend to be highest in the winter when we have heating loads and not so much hydroelectricity. And in the Southeast, where there's a lot of electric resistance heat, there's also a lot of winter peaking utilities. So there's a lot of value. I would think a lot about AC as being a peak load today, and that's still very much the case. We have an increasing number of utility regions that are already or moving to winter peaking, and we need to think about how do we make that winter demand flexible and maximize the use of the clean energy resource that's available on the grid and that we're continuing to develop. It's also reducing operating costs, as I mentioned, particularly for customers who have time of use rates. It's better comfort. You can avoid the defrost penalty, either the fact that you have cold air blowing, or you have to use electric resistance element to smooth other defrost events when the air-to-air heat pump is in defrost mode. You can use hydronic heat to do that much more efficiently than you would with strip heat. And then it's also compared to a lithium-ion.
Derek.
I think we have somebody who's talking at another meeting. So you could do all that with a lithium-ion battery, right? The only difference is a lithium-ion battery will cost 10 to 15 grand instead of being a hot water that most people have anyway, and that you can turn into a smart battery with a controller. And also it's much more durable and much more efficient. The round trip efficiency of the thermal battery in harvest system is about 95% compared to about 90% for an electrochemical battery when new, and electrochemical battery, both efficiency and capacity will degrade over time, whereas a thermal battery does not degrade over time, right? So I think electrochemical batteries are great for electrical loads, and thermal batteries are better for thermal loads. And that's kind of the message and the concept that is driving the Harvest Thermal company. So how do we do this? Thermal storage is often thought about as with the phase change material or PCM because they have high storage density. But we can also achieve high energy density with a water-based battery, sensible storage, so latent storage. And the way to do this is to have high temperature differential between charge and discharge temperatures. And in our thermal battery, we have about 70-degree temperature delta between the hot water supply and the return from the heating element, from the air handler. And that allows you to have around 7 kWh of capacity that if it dispatched twice a day in the winter, so it's about 14 kWh of dispatch energy every day in the winter, which is more than you get from a Tesla or other electrochemical batteries, which typically are discharged down to 50% capacity once a day. So you get about twice as much dispatch energy with this thermal battery than you would get with a typical electrochemical battery. So load shifting results in the field. So here's a diagram of an entire quarter for one site. And you can see that in the green bars are the energy use, or green and no other colors, are basically the energy use from the heat pump, the air handler, and the controller. And the background is the time of use rate schedule for a PG&E customer in the Bay Area. And you can see that 90% of the load was shifted off peak for an entire quarter. So that's where the time, the cost savings come from the customer. 80 to 90% evening load shift on average, and that leads to about 20 to 30% cost reduction compared to gas or compared to a regular heat pump. And then with hourly dynamic price, which is our next frontier, which we were participants in a CalFlex Hub project funded by CEC and managed by Berkeley Labs. And they send us this price signal. So the bars are a little confusing because the bars now on the second chart are the prices. And you can see the prices vary twice a day, to peak, morning and evening, just like when the grid gets more stressed. The orange curve is the thermal demand, which is mornings primarily because of heating and evenings as well. And then the blue curve is the electrical demand from the system, which is reshaped to be primarily on sub 10 cents a kilowatt hour. So to give you a sense of magnitude, the average cost in PG&E of a kilowatt hour is about 40 cents. And that time of use, that hourly demand varies from 5 cents on the lowest times and up to $1 a kilowatt hour at peak. And that is, it's not quite $1 on this chart, but it's pretty high. And if you are able to maximize the off-peak price, you can basically make your system very cost-effective. This is a test price. It's not an actual price, but PG&E and the other IUs in California are rolling out a real-time price pilot with customers being able to enroll in the real-time price starting later this year. And we are working to be able to integrate and offer our customers the ability to participate. All the harvest system, we have over 200 systems in the field today. They are all already equipped with the technology to respond to the price signal. So it's basically ready to participate to any utility that or program that has the ability to send a price signal to customers and to compensate them, or basically to make them pay their electric rates on the price signal. You want to optimize for what people pay, not if they still pay for a flat or time of use rates, then it's not going to be aligned. But it's already, as soon as those price signals are available, we'll be able to enroll customers. So last slide. Oh, so not one more before last. In terms of markets, this is targeted at system homes with individual heating and hot water units, which is both residential, single family, and low-rise multifamily. Think garden style apartment where units are in a maybe multiple units per building, but each unit has their own heating hot water system. It supports both retrofits and new construction. We have a picture of a KB home unit here that has a harvest thermal system. And the system supports both forced air in central air, as well as hydronic mini splits, as well as radiant in-floor radiators and baseboards. So connectivity, I just want to finish on this slide and open up for discussion here. So the harvest pod is the device that does the optimization, that receives the price signal, processes it to basically identify how this price signal can be blended with other sources of signals. That can be a greenhouse gas signal. It is the weather forecast that influences the efficiency of the system, and how you blend those different signals into a single price signal, and then segment it into charge-discharge periods. And then that's schedule the heat pump to charge the tank on those lowest price times and discharge it on the highest price times. We have two pathways for connectivity. We have the Wi-Fi. Well, it's not necessarily Wi-Fi. It's internet connectivity at the device, which can be either customer premise internet connectivity in single-family homes, or a building level independent from tenant connectivity for multifamily buildings, where we're going to set up a network across the building to connect the harvest systems to the internet, as well as EcoPort, which basically provides the connectivity at the device for any utility or program that is ready to send the CTA modules and provide a signal on the CTA or EcoPort modules. So far, we haven't had any applications, but we are ready for it. And the goal, I think, of incentive programs in California, like SGIP, requiring this is to make sure that we build critical mass to have enough EcoPorts in the field to make utility programs worthwhile. So we have these two access points. So far, we've been using the API as the primary pathway, but we can respond to both pathways and ready to acquire both time of use and hourly dynamics price signals. So with that, I'm going to, that's all I wanted to share with you, but I'm happy to answer questions and start the discussion.
Thank you so much, Pierre. That was awesome. Love the slides, especially all the visuals too. Made it super clear what was going on. I'm sure we have a bunch of questions.
Yeah, Pierre, thank you so much. This is great. There is a question here from John that wants to know if the harvest pod is locked and loses power or connectivity, does it continue to maintain those TOU rates?
Absolutely. The time of use rates are in non-volatile memory, so there's no issue. The pod is really an autonomous control device. It does not need to be connected. The system will function perfectly well if you are not connected to the internet. It will obviously not have the weather forecast and not have the hourly dynamic prices, so we'll fall back to the built-in time of use schedule if it's not connected. If it loses power, you will still be able to get hot water. You won't get heating because the circulator pump is in the pod, so if there's no power, there's no circulation, but you will still get hot water, and the Sanco 2 will still be able to operate without power. It just won't have the time, the load shifting. It will just be operating like a regular Sanco 2.
Okay. Other questions from anybody?
Sorry, if the Sanco 2 loses power, it won't operate, right?
Yeah, so if Sanco 2 loses power, it won't operate for sure. Heat pumps do need power. I mean, they're super efficient, but they still need power. But you do have a 120-gallon storage tank at 150 degrees. That's equivalent to about 200 gallons of 120-degree water. That can take you several days through a power outage. So I actually tested in my home, got hot water for about a week on a full tank. So it's pretty resilient to power outages. So that's a benefit, yeah.
It's amazing. Tristan, you have a question?
Yeah. So it's actually a great time, since this is a connectivity meeting, to kind of ask Pierre a more complicated question. And Pierre, I'll give you a head start so you can think about your answer. So when a device goes offline, the question is, how much of a good citizen is it going to be for the grid? And historically, water heaters that are completely unmanaged have been really, typically coming on right after use, 6 to 8 in the morning, 4 to 9 at night. They're kind of bad citizens when they're completely random and unmanaged. And so any kind of sort of schedule, and certainly J13 and Title 24 of California was on its way to doing that kind of thing. Obviously, if a device is connected, it can respond to daily price shape changes and the blend of signals that Pierre has talked about. So Pierre, my question to you, and then I'll give a little bit more detail, is you talked about a default time of use schedule, but once you start absorbing sort of daily price shape changes, have you thought about whether instead of a default time of use schedule that maybe for at least a week or 2 or 3, kind of responding to the last price shape, signal shape you got might provide better citizenship, maybe the wrong word, than sort of a time of use? So if you could think about that, and then meanwhile, I'm going to just give a little more context to everyone else, right? As we develop more and more connected devices, the question is, how are their signals getting to them, and what are they going to do when they don't get a signal? With obviously for water heating, domestic water heating, going back to random would be kind of the worst behavior. And certainly a lot of signals are often sent only at the event time, right? And so the question everybody should ask of service providers, aggregators, and all kinds of things is, hey, is there any way to get signals in when devices are connected? Because they're not always connected. Can we preload a lot of months of good behavior before things go bad if they're unconnected? Can they buffer their data to prove that they did for M&V? There's a whole bunch of stuff about connectivity that I'm starting to present at conferences that are worth thinking about now that we're sort of moving beyond the basics. So with that sort of preamble, Pierre, what are your thoughts?
Thank you, Tristan. I would not expect easier questions from you. So I hear two things here. One is about, how do we make a default behavior smarter over time when you don't have connectivity? And the other one is maybe a little more about emergency or events and how to make sure that they are optimized for the device. Actually, that's one thing I would like to talk about. I don't know if it's exactly your question, but so on the first question, we could try to learn from hourly prices and use that learning to create a default that would be closer to the hourly price than the time of use. Today, we don't do that. What we do is we set up the device as part of commissioning, as required by J13 for a time of use rate that is suitable for the customer. So it could be, a Portland General Electric time of use rate, San Diego Gas and Electric time of use rate, whatever utility the customer is in, we select the time of use rate that works for the customer. That's the default that the system will fall back on when not connected. On learning and making that default smarter, I think it's definitely a good idea. It's also not easy to implement. It's not just about what was yesterday. You have seasonal differences. You have differences between weekdays, weekdays and weekends. So it's actually it would be fairly difficult to do this. I think, you have machine learning and technologies today that can do this sort of thing, but they need a fair amount of data to be able to be smart enough. So I would say it's maybe something you could do after a year. I don't expect you could do it just after a few days in any way that would be significantly better than a time of use. So time of use is still, it's not great, but it's not perfect, but I think it's still good enough for a large extent to be a good grid citizen, if you want to be a good enough grid citizen. And then the question is, can we make that even better? Yes, for sure, over time. The second point I want to make is for this technology works best when you have a day ahead price signal, right? Because you need to be able to charge ahead of time. If you just get a shed signal and you haven't had time to load up your tank before then, you don't have much energy to shed. So, if we just load up and shed signals from the cloud or from, whatever utility server, and you don't have awareness of the state of charge of the battery or the demand forecast, you're not going to do as good a job as the local control controller does, right? So the way, so that's why we're not today participating in programs like Water Saver or Smart Shift, which are great programs. I think they're really doing a great job with regular heat pump water heaters, but for our system, they will actually get lower performance than we're getting by optimizing locally, because we have access to so much more information on the system state of charge, on the demand forecast, than a cloud we haven't having the level of data that we have locally would have. So the best way to manage our systems is really to send a price signal, to expose the wholesale cost, whatever price shape you want to expose to the device, and let the device optimize for it. You can still override this with grid emergency signal, saying I really need to shed everything right now, and then you're going to override your price signal and get the device to shed whatever you can shed without, or even with impacted customers. But that needs to be a second and emergency behavior rather than the default behavior.
And just as a quick follow-up, Pierre, you mentioned that price shapes and then even GHD price and temperature signal blend. But do you like the CalFlex Hub idea, which I think currently stands as around 4 p.m. the day before, you would get a midnight to midnight price signal shape for the next day? Is that the right sort of pre-planning that you want, or could you envision that you could take the price shape signal at midnight, or do you like the 4 p.m. idea? Just some thoughts on that.
No, I think the best, and I think CalFlex Hub works by setting the 24-hour day ahead signal every hour. So every hour you have visibility in the next 24 hours. Do we really need 24 hours? Not really. We could really, 12 hours would probably be sufficient or good enough. But if you have 24 hours of day ahead price signal, that's the best. If you can only send it once a day at midnight or 4 p.m., whatever time, that will still work. You just at some point you're getting short on what's the window ahead that you're getting. So you won't be able to optimize as well if you have a shorter window, but it will still work to a large extent. Ideally, you want a day ahead every hour.
And so again, you just said you receive potentially a new shape every hour. Does
Correct.
it significantly change? That sounds like pretty stressful if suddenly the new shape has a significantly different low and peak price time than the old shape an hour ago. Is that really what's going?
I mean, I know the changes between the different shapes, I think Tristan's gone offline here, will be maybe sudden, but typically will be more progressive, every hour. It doesn't matter. I mean, the algorithm basically re-optimizes every hour. It runs every hour with a new price and say, okay, here's the best, best schedule based on the latest information I have. This is the basis of model predictive control, and this is what we've implemented. So it's a fairly common way to optimize. It's basically to re-optimize as you go on a regular basis, whether it's every hour or different frequency, based on the latest information you have, and then to adjust the behavior of the system based on that. I see a couple of questions in the chat. Shall we try and address some of those?
Yeah,
Sure thing.
There's
Jackson,
one. Yeah, sorry, go ahead.
I was going to say Jackson had a couple questions and a comment or two. Jackson, do you want to come off mute and provide those?
Yeah, sure. So my first question is, I think the input to the optimized process is, price GHG, Midas type signal, which is great. But the other component, which is frankly equally and practically in some cases more important from a consumer experience perspective, is the draw profile. So
Yep.
The first question is, how do you handle the draw profile, which obviously can affect the strategy?
Absolutely, yeah. Yeah, so this is great. We have a lot of sensors in the pod that for control purposes, this is how we are able to control the different components. And those sensors give us the minute by minute draw profile for both heating and hot water every minute since the system was installed. So we are able to use this with some relatively simple machine learning to basically construct the demand forecast for the next 24 hours. the day you install the system, you have a default load shape in there, which is maybe incorrect, but it's a default. It's actually pretty high because you want to make sure that people have heating hot water days installed. So you're going to basically load up your tank as soon as you can. First 24 hours not going to be optimized. It's going to be basically as much as you can eat. And then after 24 hours, you start seeing patterns emerge. I mean, they're going to be pretty rough for the first few days, and then over time they get better and better, and you're able to see differences between weekday, weekends, weather-related differences, how it correlates with temperature, wind, solar gains, and all this stuff. And each home is going to behave differently, particularly from a heating perspective. If there's a sunny day and have a lot of west-facing glass or whatever, it's going to behave differently. We don't know the energy model for the home, but we can see how the home responds to the weather.
Right.
And that's basically internal algorithm within the Harvest Pod that monitors and uses that to build a demand forecast.
That's great. Okay, so the second question is, I saw a diagram saying that the water's heated to about 150. From my personal experience, when I heat my heat pump water heater to 150, the losses are pretty significant. And I thought I heard you say that the system can store energy for a whole week. So is that what I heard? I mean, the installation must be incredibly efficient.
Yeah, so it's correct. So we actually have specification for installers to insulate the tank in addition to the factory insulation. So we have a R10 blanket that is installed by default, and we have pretty stringent specifications on pipe insulation as well. And the water is going to lose heat over time, but the temperature is going to drop from 150 down to 110 over the period of roughly a week, right? So you can basically gets enough hot water. It depends on the draw, right? If you draw a lot of hot water, it's not going to last a week. If you draw a little bit, but basically we are able to maintain usable temperature for up to a week through a over insulated tank, and that's really important to make sure that the capacity and the efficiency of the thermal battery is where it needs to be cost effective. Is to have this more insulation than the minimum required by federal standards.
Yeah, actually, I do that too. My both intake and output pipes are. I ran some experiments about insulating them because the losses of copper pipes for heat is pretty significant. Thank you.
Yep. Other questions?
Yes. This is so just curious hearing about that loss window for like a week. So I'm curious, in storm events or if you have an outage on the grid, does that draw right afterwards? Would it spike right away as it tries to recoup itself, or would it draw out a little bit so it's not such a big pull on the grid as it's coming back to life?
Yeah, the black start syndrome. Yes. So, well, it depends on the state of charge, right? If you still have enough hot water in your tank, and you're on a peak period or high price period, the system will just wait for the low price to start recharging. If you're low on state of charge and you've run out of hot water in your tank, we're going to prioritize customer comfort. Unless we get a grid signal saying emergency and don't use power, so we can respond to that. But the default behavior without a grid signal saying wait until you start will be to start right away to make sure the customer service is restored ASAP. But we always prioritize for customer comfort and hot water delivery first, and then for load shifting, unless told otherwise from the grid operator through the grid signal.
All right, thank you.
I just wanted to add to that because again, we're the connectivity meeting. So the CTA 2045 committee has started meeting again, and it'll probably be at least a year before this comes out. But water heaters, as you know, if they've been off for a week in a hurricane area, they're all going to come on at the same time. And meanwhile, if you haven't had hot water for a week, the idea that you're going to start heating that water tank 15 minutes, 25 minutes, 5 minutes later is no big deal. Now, historically, for the module makers that are on the call, we've been asked, hey, can you phase in the water heaters? And what happens that we've told everyone is a lot of times the tank will boot up, power up, turn on before our module boots up. I'm not speaking for all the module makers, but to really make sure that we're solving this black start problem, at least for water heaters, we're thinking that we would encourage the manufacturers that when they get powered on, they have a way to wait a few minutes, 2 or 3 minutes would be enough. And then maybe they even have a randomized event. Now, obviously, if you're troubleshooting it, you want it to start right away. So there should be a troubleshooting mode. But yeah, if water heaters would wait a little bit or have randomized start, the module would boot up and say, hey, I've now communicated to the grid and I'm going to change that. That would be super helpful at scale for water heating. So we're working through those ideas. If anybody wants to add to either what I just said here or in the committee, all good. Thanks.
Yeah, I think maybe related to this, Tristan, is could be a soft start strategy. Like, the Sunco 2 doesn't have electric resistance, so it's going to start in heat pump mode, and you're only going to draw a kilowatt or so, right? So, but it's a lot less than you would if you fire both elements. But there could be a way to soft start until you reconnect to the grid.
How low is the Senko operating down to, Pierre?
Low in terms of what, outdoor temperature?
Oh, in terms of ambient temp.
Yeah, it's spec'd to operate down to -25 or -27 or something like that Fahrenheit. We haven't tested that, although it's coming soon. We have a couple of systems deployed in Edmonton, Alberta. So We'll see very soon how this works. But so far we've gone down to about 0 on some of our customers, and we've been able to verify very, very little, if any, capacity loss down to those temperatures.
Amazing. Wow. Okay. And then I guess my second question, sounds like the water lasts a long time. I think an average household uses like 45 gallons of hot water a day, or that ballpark. But then using the water for heating, it's basically heating as well. Is there an indication for like an average size home for, let's say, raising the temperature every 1 degree or every 10 degrees Fahrenheit? Like how much hot water is that using?
Yeah, I mean, there's an average, but there's no typical home, right? It varies a lot. From some homes have a lower heating load than a hot water load, and some homes have 10x the heating load than the hot water load, right?
Wow.
And it's a huge range. It really depends on home efficiency, on customer behavior, on climate, of course. There's so many parameters. It's so variable. But it's at the end of the day, we offer 120. We offer 7 kWh of electrical equivalent, storage capacity, and that may meet 100% of people's needs, or that may meet only 50% of people's needs. It really depends on the home, and you can actually get 2 storage tanks gang together in series, like you do for multifamily. And that will provide more storage capacity for people who want it and who need it. Obviously, there's diminishing, marginal benefits to the second storage tanks, but that's definitely possible for high demand homes. You can also do 2 Sunco 2s gang together to provide higher capacity. We do that a lot on radiant homes, ICLers, which have higher heating loads than what single Sunco 2 would be able to provide. So provide 2 Sunco 2s, 1 or 2 tanks. There's lots of backup strategies that are possible.
Awesome. Thank you.
Okay, I think obviously, Pierre, we could probably go on for quite a while with this, but I think at this point we should terminate the conversation. There's been some other chatter here regarding participation in the CTA 2045 committee. I'm going to let Tristan and Eric and Joe orchestrate that. As many of you know, I'll be retiring at the end of the year, and so those are the people who are going to stick around for running this. But anyhow, other conversations, other topics. We've got a good portion. We got as high as 50 people on the call. Any other topics that you want to bring up, or other topics you want just covered in future meetings? Don't be shy.
I can let folks know what's on the agenda for the next couple, and that might help inform as well, and spark any other ideas. But Karen, who is going to present today, is going to be presenting in December for our final working group meeting of the year. So she'll be talking about the Cocoa, Florida collaboration study between FSEC and PNNL. And there are 3 reports that have been released there. A lot of them were for ACEEE in various years from 2022 to 2024. Those are all in the meta-analysis sheet that I think many of you have access to and I've spoken about a few times before. So there have been some really innovative load shifting research there. So that study will talk about mostly CTA 2045A in the field, but also CTA 2045B in the lab. So kind of seeing what the difference is there. So that's on the docket for December. And then for November, we're actually doing something a little bit different. We have Sam Rosenberg, and I believe he's at PNNL as well. And he's actually going to be talking about an HVAC load shifting study, which is, so kind of a little bit in line with what we had today, but just kind of expanding our scope a little bit to, look at HVAC loads a little bit too, and see what we can learn from that for heat pump water heater load shifting. And that study actually took place in Cordova, Alaska. So talk about stress testing. So that should be an exciting meeting for November. Definitely want to attend that. And then, just, see how well, space heating heat pumps are able to do load shifting too, because there are a lot of strategies there. We want to make sure we're not just thinking about heat pump water heaters in isolation, but as part of the entire home load that we're able to shift.
Good overview. Great. Well, I think we should wrap things up here, and Tristan and Noah and I and Eric are going to chat briefly before cutting this off by 10.
Awesome. All right. Thanks so much, folks, for attending. That was great. Thanks again, Pierre. Awesome presentation, and hope to have you as a regular at this working group again. I think you're muted.
Yeah, I would love to, and thank you all, and Jeff, good luck, and
thanks.
Thank you for all your work.
Absolutely. Happy to do it. It was an honor to do it. So, okay, and yes, the PSU conformance testing report is near ready to be out in the world. I can send you a copy. If somebody has a personal request, reach out to me, gwicks@nia.org, but it should be posted on the web hopefully next week.
No, I think